Okay, hello again. So last time I showed how to get to the Black Scholes PDE step by step. So remember, it's given by this parabolic partial differential equation. And I want to get to solving the equation. But to get there, at least the way that I know how to get there, we need to know a few other things, and putting that all in a single video would just be far too long, I realize, so I'm going to split it up. And the two things are the Girsanov Theorem, and then I think I'll also do one on solving a geometric Brownian motion, SDE, because that can be important. You need it, and I decided instead of just assuming and writing, it might get confusing, so I'll do another video on solving that too. But that's easy, and it'll be fairly short. But anyways, this video will be about the Girsanov transform, at least how it's directly applicable to this. Obviously, the full theory, is far more in depth than we need, so I'm just going to present kind of the main result that we need and then show how it can be used. So the important thing to know from the Girsanov theorem is that it basically tells us that any p Wiener process that is under the objective probability measure p. So in all the previous work, whenever I had a Wiener increment, gotta go way back to when we still had randomness, like here, for example, I was just writing W, but there was an implicit, at least at this point in the derivation, we hadn't gone through. Here we effectively changed measures, which is why we were led to having a drift of R in the end. But at this point, there was kind of an implicit P right here, denoting that we were under the objective probability measure, or the real-world probability of P. So, going back to Girsanov, it tells us that we can write, so if we take let's take a increment of a Wiener process under real-world probability. We can rewrite this as some phi not a good phi. So it's like it's phi in LaTeX. It's called var phi. Dt plus then a Wiener increment, but under risk-neutral probability Q. And this phi is often called the Girsanov kernel or transformation. So we saw, and now I'll show you how this can be used. One example is, so we saw before that when we go through the Black Scholes PDE, we are left with R as the drift. So let's prove that instead by using Girsanov's theorem. So take the standard dynamics of the underlying. So we know that it was given by a geometric Brownian motion but instead we are going to consider the discounted price process. So if you think of it, a normal discounted price of the asset, what's it going to be? well, normally, so we're in continuous time here, so continuous compounding, you would normally think, you know, exponential of negative rate times time times the underlying. Now I guess we're going to consider it more so in the form of so this would obviously be equivalent to S of t over e to the rt. And what is e to the rt? Well, we're assuming that this is the bank account or the bond. So the point there being is that when we say we're going to consider a discounted price process, what we are going to consider is the underlying ST over BT, just to make it a simpler form. So considering the discounted price process, what is D ST over BT? That is a B. So to do this, we need to remember the Ito quotient rule. And that tells us that if we have d of some x over y, that's equal to x over y times dx over x minus dy over y minus dx dy over xy plus dy, sorry about that, dy over y squared. So with that, we just fill in, obviously in our case x will be st and y will be bt, the bank account. So let me write this out. Bond equals, so we'd have, to fit this in, I'm going to drop the t's for right now. So over b times ds over s minus b over b minus ds db over sb plus alright, so to simplify this greatly, what do we know already? Well, if we remember the product rules, we know that any dt terms squared, any dt dwt, any dwt dt terms fall out, and in terms of squared terms, the only thing that remains is when we have two Wiener increments multiplied together. Independent Wiener increments simply become dt. So why is that important? Well, we quickly see that these terms would just completely drop out, because we have the stock increment here times the bank account increment. There are going to be no squared Wiener increments there, and likewise here, if you recall, the dbt is given by rt dt. So you see, squaring that, you're going to have a dt squared term, which is, you know, again, essentially 0, so it drops out. So that means that these two terms completely drop out. So, with that in mind, let's start to actually work through that. So, what you would have here is the differential st over bt is equal to, it's going to be d st st. So I'm bringing the, here I'm also bringing that in. That's where that st comes from. dst over bt st. So obviously these quickly cancel. Minus st over bt squared dbt. I guess you could, to keep form consistent, put the dbt in the numerator, but whatever. So with that, we will start to fill some of the stuff in. That is dst and dbt. Obviously we know those. They are assumed to follow certain, so dst follows a certain STE, the geometric Brownian motion, and then again I just kind of gave up here the way that dbt looks. So let's fill some stuff in here. So we're going to get d, I'm going to drop the t's here to save a little room, equals, so we have 1 over bt times, and then I'm going to fill in the underlying stock dynamics. Fix that a little bit. Alpha st dt plus sigma st dw. Again, I'm going to keep the p so that we don't get confused here. And then we're also going to have minus st over b t squared times r b t dt, where we quickly see that this bt drops out and this power of 2 drops out then. Now this is the same. This is equivalent to d so over b being equal to, so if we simplify all those terms, simplify all this, we will find that the differential of the discounted stock price is equal to 1 over bt times alpha minus r s t dt plus 1 over bond sigma s t, and then the Wiener increment still under p. So this can be thought of as the discounted price process, still under the real world or objective measure p. Now is when we're going to invoke that Girsanov result, that the Wiener increment can be rewritten as such. So invoking this, what's going to happen is, just thinking how to rewrite this to all fit in. What I'm going to do is I'm just going to show you how this term would be rewritten. So that, of course, is just going to become 1 over bt sigma st, and then times the Girsanov result of phi dt plus the Wiener increment, but now under measure q. So, doing that, so writing that term instead as this, if we then simplify all of this now, what we would be left with is that d S over b is equal to 1 over bt times alpha minus r plus phi sigma s t dt plus b t sigma st dwq t. So now what do we want? So we want this to be a Q martingale. How do we do that? Well, you can do it by making this term equal 0, right? Because then the dt term will fall out. And you know, this part is a martingale, so we'd be left with then a Q martingale. So in that, to that end, let's do that. So we'll say that we want alpha minus r plus phi sigma equal to 0. So in solving that for the Girsanov kernel phi, we find that that needs to equal r minus alpha over sigma. So that is our Girsanov kernel. So why is that important? Well, we now know the Girsanov kernel, and we know the whole big result of Girsanov that we can write. Again, I'm here again. That we can write a p Wiener increment as such, but now we actually figured out what that phi is. It's given by this. So with that, that means that we can go back to our standard p dynamics and change them to be under measure q. So again, recall, I'll write it here so that you don't have to go back. Remember, we're just under the standard geometric Brownian motion, st dt sigma s t, and then because we have alpha here as the drift, we're still under the objective probability. Now let's invoke Girsanov and also that derived kernel. So we would have ds, drop the t to save room, equals alpha s t dt plus sigma s of t, and now we have r minus alpha over sigma dt. So remember, this part is that in Girsanov it's phi dt, but we derive that right here, the phi, plus a Wiener increment, but under measure q. So what happens here? Well, what we're going to end up having as, if we collect dt terms, when we collect dt terms, you'll see that what we'd have is that we'd have alpha plus r minus alpha over sigma times sigma s t dt. So what happens here? Well, obviously these cancel, and then your alpha is going to cancel, and then lo and behold, you're just left with r st dt. So that means that the final dynamics, so that was basically all of this stuff. So writing in the final dynamics then, we're going to have ds t equals to r s t dt plus sigma s t plus a q Wiener increment. So we are led to the same result, that under Q, the risk neutral measure, the drift of the underlying changes from the underlying specific drift alpha to the risk-free bank account rate R. So that's an important theorem to know moving forward. Not necessarily this application in particular, given that we already, essentially knew this when we derived the PDE and found, R here. Why it's important to know is to find, other types of dynamics. So one I'll show you now that's important for when we eventually solve the PDE is what I'm going to call the QS dynamics. And what is this? Well, so we had, before we saw S over B. And this is often called the numeraire asset. So it's like a normalization or standardization asset. So the Q dynamics are given when we have the bond as the numeraire. The QS dynamics are given when we have instead S as the numeraire. And again, you'll see why that's important, why we even need that when I eventually solve the PDE. But for now, I simply want to show you what the QS dynamics are, because then when I get to that part in that video, I'll be able to just give the result and refer you to this video to save time. So for the QS dynamics, let's instead, we just saw ds over b, let's flip it. Let's consider d of the bank account over s. So now we have s as the numeraire. So if we recall the Ito quotient rule, have it up here. So to save some space and time, I'll tell you right now that in this case, you remember here we had the cross term and this term both fell out. Well, in this case, with s as the numeraire, only this term is going to fall out. We will have this term because obviously in this case y is actually s, and the dynamics of s obviously do have a Wiener increment squared, so that will remain. When we do that, and if you want to rigorously confirm all this yourself, go ahead, but I'm going to save a little time. Basically what we'll have here is we'll have b t over s t times r bt dt over b t, those quickly drop out. then we're going to have minus RST. So these are the Q dynamics. So what we're doing here is, to be clear, we're getting the QS dynamics from the Q dynamics. So the Q dynamics, given that we're subtracting here, I'm going to write a minus here. So you understand that why those two are minuses. ST, so the ST's cancel. And then you would have the final term, so this is the dy over y squared term. Obviously we have something here. So what are we going to have? Well, we would again have the same thing as I just wrote up there. Leave it like that. So those are going to cancel out of that again, and we'd have that squared. And it'll get closed off. Obviously this part, so we know that this dt term squared is going to completely fall out, and this term obviously is just going to become sigma squared dt. So, simplifying all of this, what we are going to have is d, I'm going to drop the t here for a second, equals bt over st, so we're going to have r dt minus r dt, nice, let's drop out, minus sigma wq t, and then plus sigma squared dt, as I just showed you up there. So that means that the write this now as totally final form equals bt over st sigma squared bt minus bt over st sigma dwqt. So that is this. It's processed with S as numeraire, but still under the Q, the measure Q. Now remember, our goal here is to change from Q to QS. Now Girsanov works just like it did before. We'll just change the notation a little bit. So Girsanov will tell us here that a Q Wiener increment can be written again as some process phi. I'm going to superscript it with S because we're changing to the measure QS here, dt, plus dw, and I'm going to say QS. So this is effectively analogous to the, let's see, where is it? Here. So we were going from P to Q. We had this. So you see it's entirely analogous. Same idea. We just changed the notation a little bit to denote that now we're moving from Q to QS. So, with that in mind, we can find the Girsanov kernel by filling this in. So recall we had equals BT over S of T sigma squared dt minus, and then we had BT S T sigma, but now we're going to rewrite this, because you remember at this point we just had dwqt. We're going to rewrite that as this up here, phi superscript s dt plus dwqs at t. So simplifying this, to save some space, I'm just going to show you how the dt terms collect. Those would be collected as bt over s t times sigma squared minus sigma phi dt, again, just like before, to get a q s this time, martingale, we are going to set this equal to 0 to get the Girsanov kernel in this case. So setting sigma squared minus sigma phi to 0 and solving for that phi s, you're going to be led to that phi s equals sigma. So this is the QS kernel. So now, again, we're going to go back to the standard underlying dynamics. Important to recall that this time we are starting, again, we're moving from Q to QS. So in this case, when I say standard dynamics, it is the Q dynamics that we derived before. And we are going to invoke Girsanov, which tells us that we can have dst equals rst dt plus sigma st. But now again, we will invoke Girsanov with the kernel that we just derived here. So we will have sigma dt plus dwqs t. So simplifying this, we will find that we are finally led to dst equals r plus sigma squared st dt plus sigma st times a qs Wiener increment, which for practical reasons, it might be important to note. When I have like dw under p, dw under q, dwq under qs, practically there's no difference. So these, or this, is the QS dynamics. Wow, that was quite poor. QS dynamics of S. That is when we have what's called numeraire asset as S. And just to have it all here, recall that we also had D, which we already effectively knew from solving the PDE. RST dt plus sigma ST dW Q. These were the Q dynamics of S. So these will again become important when we eventually solve the Black Scholes equation, at least the way I'm going to show you how to do it, which will be in 2 videos. Next I'm going to do another, calculation you need along the way, I don't feel like first assuming that everyone just knows it, at least the way I know how to do it, and also that I don't want to bog down that video with a 10-minute ancillary calc. So I'm going to show you how to solve the geometric Brownian motion SDE. But anyways, in 2 videos, when I show you how to solve the PDE, I'm going to use the Feynman-Kac theorem, which will effectively have me splitting the payoff function into 2 pieces, and then solving each. And in order to, basically use some nice properties of indicator functions, I will, at certain points need to invoke these results and the QS dynamics of S. But anyways, it's probably too much for now, and it doesn't make any sense until I actually do it. So thanks for watching, you 2 people, if I'm lucky, and I'll get to the GBM now.